Thanks everybody for joining us today on July 14, 2020 for the Light Up Virtual Conference, 24 hours of Microsoft technology learning and fundraising to fight COVID-19. We'll be talking about Kinect for Azure for developers. My name is Andreas Erben, and you can, that's important, take a picture of this slide. You can donate in support of Unicef to fight this COVID-19 crisis. Every contribution matters. We will probably go back to the slide at the very end, and you can also go to the Light Up Conference website to get this donation link. We have a bunch of great sponsors. I will not read all the names individually, but without sponsors, an event like this would be impossible. So thanks a lot to every sponsor. Thanks also for C# Corner and to the tech platform to facilitate and set up this event. My name again, Andreas Erben. I'm the CTO for Applied AI and Mixed Reality and CEO of Americas of DNet. I have 25 years of experience in this field and have been dabbling with VR and interactive user interfaces already in the mid-1990s, but then a lot of years there nothing was happening. I worked with companies of all sizes and all types, from startups to big enterprises. So, but I love geeky technology. My contact information is there if you have questions. You can also contact me after this event if we don't cover anything you are interested to learn more. Talking about the Kinect Sensor a little bit, right? I believe my camera feed is shared, and if not, then I will go back to it again. This is the Kinect Sensor I'm holding into the camera. It's a little depth camera that has, as you can see, some light emitter, and you see probably some speckles and pixels on the camera and on the camera sensor, and has a few cameras in there, has connectors for USB-C, has additional connector for power. If you would unscrew this, it would have another connector for synchronization. But I have a lot of content to cover, so let's go back to my slides first, and let's look at what is the history of Kinect. Kinect initially was released for the Xbox 360 as a complete pure gaming device for motion control, video games, and so on. But hackers, good hackers, started to dabble with it and started to write applications for it. And Microsoft had a difficult question to solve. What do we do? Do we support the hackers or do we fight them? They decided to support the hackers and decided to make their API to develop Kinect software public and develop a product out of it, Kinect for Windows version 1.1, and which has skeletal tracking enabled. What that is, we will see later. With 20 joins and landmarks, which was groundbreaking at that time. Then 2013, Kinect 1 came part of Xbox One, and following 2014, Kinect for Windows V2 was released, which improved on body tracking and a lot of other things, and the core sensor technology was also changed. Finally, in 2018 was a mixed year because we learned that Kinect for Xbox One didn't have really a future, but then the project Kinect for Azure was announced. In 2019, it launched at Azure Connect Development Kit at the Mobile World Congress with new body tracking SDK and Skeletons 3.0 composed of 28 joins. So this is again how it looks like, right? Just very briefly. And if you would blow it up, then that would look like this. So I believe you can see my mouse cursor. This is the main board and all the different components of it. You see the lenses here, you see the RGB camera, and you see the depth camera, which is light emitting module, which is laser light, modulated laser light that's been emitted. And you also have a microphone array here on top where Kinect can locate sound in space and theoretically in a specific direction, or you can use it for noise cancellation of ambient sound. A little bit extra nerdy content that you can read about on this paper. So it's the public information. How does it actually work? We have a so-called time of flight based depth camera in there. It means it modulates light are coming out of light emitters, and it knows how that light is modulated. So by knowing how it is modulated and knowing the exact timing of that modulation, it can then calculate and disambiguate for every pixel that it sees for this light signal, and that is an infrared light signal. It can then know, based on this modulation, how far is something away from the camera in a specific spatial depth resolution. There are two resolution modes in terms of depth, where you get a little bit more detail on a narrow point of view, or you get a little bit less detail but have a wider field of view. This is another slide how basically some of the math inside works. Has a few other interesting factors also. Those are the sensor screens that you see from it. Has an active IR image. What does it mean, active IR image? It means that it's driven by the infrared camera light emitters of that device. It's infrared, but it's not heat. This camera cannot see heat specifically. But because of this fancy light modulation, it actually can remove ambient light from the picture. So if I would shine like another infrared source on the same spot here, you wouldn't see a bright spot coming here, because it will only show the light that it knows about from the modulation from the camera. This is a so-called depth map. It's a visualization about how far something is away. It just shows this color scheme for it. Don't want to worry about it. And it has a full color image. It has an IMU, so an acceleration inertia unit that you also would find in phones. That's very useful if you would want to mount this on a robot, for example, or get an idea which angle the camera is positioned. And here's the microphone array, the raw data. It has, well, 8 channels, no, 7 channels, sorry, 7 microphones built in. As in software stack, very, very rough. Right? You have the Azure Connect DK device that connects to your PC via your USB-C, and the PC accesses it via just regular USB protocol. There's no specific driver you're really working with. The sensor SDK accesses that device pretty directly. Speech can be processed through the microphone stream. It presents itself, or you can access the microphone stream. And on top of the sensor SDK, there are a bunch of things you can build on top of that. What the sensor SDK provides, we will look at a little bit more in detail, but you can use Azure Vision services, like Cognitive Services Custom Vision, to just look at the camera images from the camera and get information out of it. Well, body tracking SDK, we will look what that is. Is that magic where you can understand what a human body does or how it posture and so on. And then any type of user build skills that you would want to build on top of that SDK. That then is the other building blocks to build your applications. So the sensor SDK, and that's also something that old Microsoft would never have done. It's completely open source, right? So it's cross-platform and low-level access. You can write software on Linux for that. Currently, as far as I know, it's Linux and Windows, and it's not yet on Mac OS. I don't know if that will ever happen. I believe one of the challenges is that the component that is being used to calculate the 3D location, so basically the mathematical magic that works on the sensor stream and gives you the depth, that's the only part that's not open source. I don't believe they have ported that because that's also accelerated by the GPU. And then, well, all the other things I will not read through. It's accessible on Linux and on Windows. The vision is to have it eventually even on Raspberry Pi type of devices if they have enough processing power. So to not be constrained to purely desktop systems. As in languages available, you can develop most natively in C. The whole thing is written in C. There's a C++ wrapper on top of it, and then a C# wrapper. And all my samples set expectations are going to be in the C# wrapper. I will not be, by the way, I will not be able to monitor the chat myself, but the chat is being monitored by the moderators of the session, and we will have questions at the end to be answered. And you don't need to hold them necessarily, but maybe it's better to hold them a little bit, and the moderators will do it at the end. So there's tools, right? I mean, the Sensor SDK comes with tools. You can download it, you can install it, and then you have it on your hard drive. Somewhere here, like in program files, Azure Connect SDK, and there's tools. Tools is you have a tool to update the firmware, which I will not show. And you have a recorder to record, a data stream, and then the viewer component. So the viewer component, if you just launch it, looks like this. And when you start it, it shows you a list of devices. It looks at the USB bus, what are my devices? And then you open the device. When you open the device, no other software can access it. That's a difference compared to Kinect for Windows version 2, where you could have multiple pieces of software accessing the device at the same time, at the expense of having this centralized driver component and service installed on the computer. So they wanted to get rid of that. There's a bunch of settings you can choose here. Something called binning, and which basically combines neighboring pixels to get better information, less noisy, and better depth vision in that sense. And you can choose between a wide view and a narrow view. And you have a passive IR camera. You can choose the color format, the colors being encoded to, the resolution of the color stream, and the frames, how many frames you want to take, enable microphone, and so on, and so on, and so on. But let's start it quickly. Right? So this is a view similar to what you've seen in the slide, how it looks like live. Let me walk into the picture really quickly. That's me. And you can choose also between a 2D mode and a 3D mode. So you see here that it actually has maps, is able to map all this video stream into 3D space. Okay, so let me not forget to close this device. Otherwise, if I show you other code later on, I will get an error because my demo code will not be able to access it. All right. So Azure Connect, again, it's open source, it's on GitHub, and it's also the best way to report issues or to ask questions is to just do it via GitHub. You can also use customer voice to propose new features. And Stack Overflow is also a platform that the Connect team actively monitors. So rather than trying to chase down those people inside of Microsoft, who are they, why don't they help me use GitHub? And they really are pretty responsive on that. Now let's go to body tracking. Body tracking has been designed from the ground up new for Azure Connect DK. It provides what they call an instance segmentation map. It means basically give me the pixels of the image, the locations of those pixels that belong to a body. It gives you 3D joint positions for a person and gives you a unique ID for each of those persons to track temporally. Meaning if you have frame 1 and the next frame 2, you will get the same identifier, the same number for the same skeleton, even if they move around, which is important if you want to write software. The quality has been improved. It's anatomically more correct compared to Connect version v2. Has higher joint accuracy and precision, improved robustness for side view, bending, and lying. That is actually a big thing because for Connect for Windows, for the Xbox, was designed primarily to interact with the Xbox console. And so it was trained on people facing the camera, facing the screen, and interacting with the screen. So it would still track you relatively well if it looks at you from the side or if you were bent in a weird angle or lying down, but it was never designed for that. And it can track up to 15 skeletons, which is not a hard limit, but a practical limit of Connect for Azure. You can do cross-platform development. There's, I think Windows with Linux works right now. It's not preview anymore, actually. and the SDKs are available in C, C++, and C#. It runs on top of what they call the Onyx runtime. Onyx runtime is a cross-platform engine, actually, that Microsoft uses for open neural network exchange format to do AI on arbitrary hardware. But supported right now is the NVIDIA hardware platform, and you need at the least an NVIDIA 1050 Ti or better for the hardware acceleration. Yes, it also will work with the NVIDIA 2080, the newer devices, so it's not constrained to the 1,000 numbers of the NVIDIA devices. Yeah. So how did they do it? They trained it with synthetic data, right? So you have this great device here, and what they did is basically those are not real people here, right? This is artificially rendered people based on real motions of real people, and they put basically fake clothing on them, and so they know exactly for each of those artificial synthetic people, like in a Pixar movie. Think about it like this, right? So they know exactly where each point on those bodies are because it's all computer simulated, and then they projected that what they're rendering here into how would the Kinect sensor see it, like artificially, right? They try to approximate it as well as possible. How would a Kinect sensor see that exact same thing? And then train AI on top of that, right? So they get all the perfect positions. They know it's the perfect labeling. They know exactly where's the leg because it's an artificial model. And it solves a lot of problems. For example, human diversity, like all body shapes and sizes, all skin colors, all types of humans that we have in reality can be simulated in that platform, and so they can train their AI better. And they can do that also in multiple simulated environments, not just in a gym or in a living room, but also in a patient's room or in an OR operating room and so on. Yeah, so this is the fundamental approach. Currently, it is trained really just for humans. No, you cannot track your dog with it. That's a very question that we get almost every time I talk about. But it's theoretically they could enable that but they wouldn't need to build models of dogs and retrain the whole thing for dogs or other animals. To compare it with Kinect version 2, I will not talk too much about this slide. It's in the video. You can pause it and read it later on. Fundamentally, it's a newer. Now it uses a neural network compared to before. Decision Forest has a better synthetic ground truth, has improved robustness. It's supported on more hardware, on more software platforms, not just Windows. Has C, C++ sub wrappers. It, however, needs a little bit more powerful hardware. For Kinect for Windows version 2, the original Surface Pro was enough to really run it. Yeah? So that's a good example as a notebook. But now you need to have to really run it sufficiently. It's a 7th generation Intel Core i5, 4 GB memory, and this NVIDIA graphics card right here. So as for the limit on how many skeletons there are to be tracked compared to the hard limit of 6, 15 is a practical limit. You cannot really put more than 15 people into the field of view of Kinect and fit them all. That's the practical limit of it. Yeah. So again, the C API builds on top of the sensor SDK, easier to wrap around for other languages, and there's a C# API. A body frame. So how was the body represented? It's a collection of body structs. What is a body struct? It has the ID of that body that's tracked, has a joint positions in 3D, which is a vector, and has joint orientations as a so-called quaternion. I have a slide later on what a quaternion is, but it's very common in game development and 3D development because it's very easy computationally to represent rotations in a quaternion. The math behind it is it's a little bit funky. Think about it as complex numbers on steroids. This is the index map I mentioned before. It gives you the outline of a body that the Kinect sizes, and you can use that, for example, for a green screen effect to show virtual background and so on. Well, input capture, you can just capture everything the camera sees and use it later on if you want. The skeletons are in 3D, so you can rotate that image around and get 3D information for all those coordinates. The architecture, how does the whole thing work with body tracking? So it starts with the Azure Connect development kit. On top of that is the sensor SDK, and then we have the camera screens. The active infrared camera stream, which is just a black and white image, is used with the convolutional neural network and the Onyx runtime to then get two-dimensional joint coordinates. For information, there's also for regular web cameras, there's also an Onyx model you can just download, Google for it if you want, or Bing for it, that gives you 2D joints if you want to write little apps that don't need a Kinect device, and it gives you segmentation maps. Now this is still two-dimensional. Well, here the depth image comes to rescue, and it knows all about the distance from the camera in space. Then they do a step called model fitting. Model fitting basically combines those joint coordinates from 2D with the real distance in space, and uses knowledge about the typical human anatomy about how far something would be. So even if the sensor stream might be a little bit messed up, because it knows how a body is, that the arm length doesn't suddenly change between two images. So it can use that to get good approximations of 3D joints, even if there's what we call occlusion or partial occlusion of a specific joint where the camera cannot see everything. Yeah. The processing, well, you get the capture object from the SDK, and then you enqueue the capture to be processed on the GPU with a convolutional neural network, and then the CPU takes over that result, does some model fitting, and that result that ends up in a queue, and the application developer would pop the result, pop operation from that queue. Skeleton 3.0, a little bit more detail. Those are the coordinates of that you get. So it's an extension of the landmarks, has improved hand positions and facial landmarks, and so on and so on and so on. I can show here, by the way, one little quirk that Kinect for Windows version 2 had. If you would look at a body and look at the hip joint, and that body would raise their arms from low to high, then the hip joint suddenly would also move up as the arms are raised, even though the body in reality never changed. This is something that's also been fixed in Kinect for Azure. A joint definition, this is how it roughly looks like. It's a float, three-dimensional vector for the position, and a quaternion for the orientation, which is a four-dimensional float, and that gives the joint. So what can you do? And I'm sorry that I'm rushing over the content a little bit, so we have more time for show something live. It enables you to do different things. For example, kinematic analysis is analyzing all those motions and all those things you can see from a perspective of understanding what's going on with the human body. Analyze the posture. You can use it for physical rehabilitation to see, do people do what they're supposed to do, and calculate mathematically what it means in terms of the exercises that were observed by the camera. Can be used for fitness apps or for sports instruction. A lot of people ask about the golf swing. Can I improve my golf swing? It's theoretically possible. I would not recommend it purely because parts of the golf swing is a very, very fast motion where it matters, and that might not fit completely into the 30 frame maximum frame rates the camera has. But other types of sports where you want to instruct people about form, meaning the body posture among exercises, is very good. Can be used for patient monitoring. Are people where they are supposed to be and not? Are they in bed? Do they move? Or do they breathe? Does their chest move when they're lying down? Breathing doesn't stop. Or can be used for fall detection. I can talk about fall detection a little bit later, maybe towards the end. Human understanding is a different scenario, as we're still looking at human bodies, but we want to not understand something intrinsic the body does, but their behavior. How long do they stand in front of a specific shopping display? How often do they go in a specific area so we can detect them and count? We can track people as they move through space. Maybe we want to know where they are or where they shouldn't be. A very common scenario is also in industry. If you have a machine and nobody should be near that machine when the machine is running, you could have Kinect sensors that, for example, only enable the machine if bodies are only outside that radio, but not in radius, but not inside that radius. You can use it for smart spaces interactions, like which is similar to the next slide, which is human interaction. You could interact with information signs and video walls, wave to the video wall, and it does something back to you. Interactive art and performance, you could transform all those sensor data into something creative. You use it for interactive museums, exhibits, and customer sizing and fitting, machine safety. So the two last topics are pretty related in what you can do with them. Like a little walkthrough about body tracking 3D viewer. I mean, you would. Well, actually, let me use that chance actually to show you the 3D body tracking quickly. Similar to how we had the installation of the SDK, we also have the installation of the body tracker. And it's a command line app here that you install in that folder. When you install that, it's starting up. Yeah, it starts up and starts this 3D visualization. Yeah, you can move that around as I said before. Bigger. Maximize it. Let me go into the picture. So the camera starts seeing me and it starts tracking my joints as I move around. And if I change that angle a little bit, so it now sees me from the side, but of course it doesn't know the pixel on my side. So it doesn't also know what's behind me because it only sees me from the front. Yeah. All right. So from a coding perspective, how does it all start? The first operation is really, hey, give me the device configuration, verify, and start the camera. So let's start with a little demo of sensor basics. Firing images. We have, sorry, I put breakpoint here. Oh, yeah, yes, start camera. Oh, I already had the breakpoint. Sorry about that. So you see that here it tries to open the device, and I hope actually that I've finished my demo. So it tries to open the device. I would throw an arrow if it cannot open the device here. Then it starts the camera with the device configuration we're setting, which is a bunch of parameters in the API. Again, this is a sharp wrapper. So it's an operation that can take a second. Oh, yeah. So it starts the camera. Now this app owns the camera, and we can get the metadata from the camera. So we know the resolution is 1920 times 1080. And we initialize a bitmap. And then when the component runs, bitmap is so I can't move the window yet because I have a breakpoint here. But essentially what it does, it then uses the API, gets a capture object from the API. And it's null right now. Let's do something. Oh. Okay, that's Murphy's Law. Try to restart it briefly. Okay, yeah. So it receives the capture object, and it has a device timestamp, which you get from the capture. This timestamp you can use in applications to establish mass based on time. For example, calculate velocity of how fast something moves. You take the difference between the timestamps, and you then calculate the difference of movement, and you can use that device timestamp. It also identifies that image uniquely. And then what it does, it takes basically it writes the buffer it gets back from the API into the bitmap. So which is something we'll just show briefly, but I will not. I mean, you cannot really debug into it. Marks the bitmap as 30 and then displays that. So let's remove the breakpoint so you can actually see it happening. In this case here, it's just, I mean, it's pretty boring. It's actually just a video camera showing the video stream. Yeah, but the fundamentals are the same for everything. It's pretty straightforward to access the sensor basics. That's the takeaway from this. So let's look at body tracking as a more advanced example, because we don't have time for all examples that are possible. Again, the process is similar, right? I mean, you start the camera, you create a body tracker object, which is you use a query capture, which is an object you get back from the camera. And remember, here you need both the depth stream and the infrared data stream. Then you check, is there a new capture? Then it says a new capture. You queue that capture to the body tracker. And then after that, try to pop the latest result from the body tracker, which could take, could happen only in the next frame of processing. So this runs then in the background. And then you process that result. Yeah, that's how it is. The demo will come in a little bit later. So again, input capture, you get the collection body struct and the 2D body index map. This is an enumeration you get as an application developer, which is very helpful to let you do the operations based on the structure of the body. So you can say, hey, give me the distance between the between the elbow and the wrist, or the vector of the elbow and the wrist, and you know where it is pointing based on those positions of the 3D positions of those indexes, right? Again, the joint definition, I showed that. Now let's do the little demo application. So you see, here it was the same as above. I start the camera, I do the device calibration. Then I initialize the tracker, which is a component for body tracking. And then I do the sensor capture, right here. So that my breakpoint starts right there. And after that, we try to get the result from the tracker. So you see the tracker is initialized, and we got the capture object. If you look into it, you see it has a depth image, with all the goodness, and the IR image, which you can just use in your code as you want. And then we enqueue that. Yeah. So at one point we get a result from that. So let me remove this breakpoint here, so we can actually look at the results that we get back from the tracker. Yeah. So we got a frame back, and the frame actually, breakpoint here. The frame might be null, right? So that means, we're asking the tracker, but we didn't get anything back. So at the one point, the processing will delete it. Here's the frame. We got the frame back finally. I have a timestamp, but there's no body to be found. That's a simple reason, because I haven't been in the camera. Yeah. So let me remove the breakpoint. And here, so this is a video stream based on the depth image. It shows the depth image here. And now the track and it, yeah. And it in the visualizer, it sets the frame data. Now let's look at the visualizer briefly. The visualizer is basically checking the data of the tracker. Actually move into the picture, and I hope it forgets the breakpoint. Okay, I didn't forget the breakpoint. Yeah. So here's a bunch of math that's happening in the render window, and in the render window, like we looked at, hey, did I get any number of bodies? Here we got a number of bodies that recognize one body, and we can look at, now let's get that body. Get the skeleton and a body ID. We set a body color, and the skeleton is, as I said, has 32 joints. Yeah, actually 32. Yeah, and well, it's a buffer here, so we need to actually unwrap that buffer and get the specific joint we want to have access to. I mean, the API lets you do it, but again, it's the wrapper itself doesn't provide well, a good inspector experience yet. So that's one of the downsides, I have to say. And it's the body ID 1. So let's get one of the joints. Get the first joint here. So, okay. Yeah, my mouse is running out of batteries. I have to fix it later on. So we get a joint, and yeah, that's the joint position. It's a vector, yeah, and the vector with its specific coordinates, and this orientation quaternion, which has x, y, z, and w as parameters. And then so we do some process all those joints that we get. So this 3-dimensional vectors and orientations. And what we do is basically for every joint check, hey, do we also have a value of the parent, meaning for the wrist, I need the elbow to be able to draw the lower part of the arm. And then let's render those two joint positions in 3D space. Let me walk into the image. And of course, I forgot to remove my breakpoint. Apologies for that. Yeah, again, you walk into the image. It's the problem when you need to step away and to see. So it renders, like what I mentioned before. So this is a wrist joint. This is the elbow joint that renders that those lines based on this the data we're getting back from the body tracking SDK. Okay, let's go back to the slides. So let's discuss briefly an example use case, right? I mean, what can you do when you would have a system like that? On an abstract level, you have a system that's and the slides are not completely updated, I have to say, unfortunately. But on an abstract level, you have a sensor system and you have a high level of sensor processing, and then you can do specific things. Right? To the very end, you have you can do posture classification on it, and you can do something activity and fall detection. You do. And how do you do all this, right? I mean, you have a concept of the world. You have physical formulas. You have a model, understanding of the body, parameters, and there's math you're doing on that body, like calculating velocity, acceleration. Then they visualize the whole thing. Yeah? Like look at body joint configuration. What you want to do, you want to look at the tracking state if available for each of those joints. So you get some level of confidence. How well am I tracking? You want to do math on it. So you want to maybe convert it to a numerical format that convenient for the math you're doing. You want to understand the joint hierarchy, as I mentioned, the wrist and the elbow, for example, and then do all those math and so on. In general, you want to read about gaming engines and physics engines and game development. Those have the best references to do math on 3D data. Yeah. As a guidance, what I used before is I used the model from the NASA about a stereotypical body and the distribution of weight in a body. Because to do math on, let's say, the energy that's being used on the elbow joint, you need to understand the length and how heavy is the arm, upper and lower part of the arm. And I got that by looking at models they use to calculate forces on astronauts for astronaut uniforms and astronaut spacesuits and so on. Yeah? And then you make some assumptions like, okay, that the bone is typically rod shape. Then you can calculate an inertia by a formula like this. You can use muscle efficiency as assumptions to do advanced math. This is a slide about quaternions. Really overloaded, but this is a fundamental definition of a quaternion. It enables you to project things onto a sphere as a rotation to simplify it. But there are wonderful YouTube videos about it, what quaternions mean to rotation. In 2020, the best thing I can tell you, look it up on YouTube, quaternions rotations, and your eyes will be open. Yeah. Now, about the math, you can do linear motion and angular motion. Those are formulas you can use from velocity to force, work, energy, and it matters, as they will show in a second. Right? This is a video I did of an app I did originally for the old Kinect Sensor. And you see that those little bubbles represent energy calculations I did based on motion. Like the green one is the angular motion, and the yellow one is the absolute linear motion. You see they behave differently. My shoulder doesn't move when I lower the arm and raise the arm like this, but there's still energy being expended because when I move my leg, I move my arm, right? So you want to do math maybe considering both. Those different vectors, the lines show the acceleration or velocity. One thing, it is a sensor-based system, so you need to handle something called jitter. Every sensor system in the world, including computer vision systems, they do not give you consistently super precise readings all the time. There might be a difference of 1 pixel or the other between 2 frames. And if you do math on that, like acceleration, you take the difference of velocity between 2 frames, you get errors that get worse over time. Here I smoothed, I used the so-called double exponential filter. And you see those lines stay relatively, well, even as I move slowly. Now, if I would remove this filtering here, and do that same motion again, it's a recording that I'm talking through it. So you see how everything jumps around. Like, so this error and jitter would be pretty much exponential if you would do math on it. So think about jitter. Again, the last slide I will just run through. You can calculate activity. You can classify activity levels if you first calculate the energy expenditure based on the approaches and formulas below. You can do fall detection by different scenarios, thinking about, for example, how fast does my head move towards the floor? If it has a sudden fast movement towards the floor, and we know the position of the floor, and suddenly stops moving, maybe something happened. Or it could be slow fall. Maybe you just want to see, hey, a body has been on the floor for quite a while, something might be wrong. In general, fall detection is not easy as a warning because there are a lot of false positives. Somebody might go down to the floor to pick something up or take a nap, and it's difficult to distinguish from an actual fall. Or somebody might jump on the sofa on the bed because they're tired, and that jump might be classified as a violent fall. Posture, also very simple or very complex. You can use advanced machine learning, or you can make very simple assumptions. You want to detect the posture? Well, look at the angle of your leg towards the floor. angle of your leg towards your hip, and you get some information. Like if it's like relative, if your upper leg is like this to the floor, and your lower leg is like this to the floor, and your spine is like this to the floor, maybe you're sitting, as an example. Posterior template, I'm skipping over that, and then this is a summary of all the math I did in a previous application. I validated energy expenditure estimation with the real heat sensing and motion sensing armband. The gold standard would be measure the CO2 that I produce when I exercise, but I didn't have that. And I found that what I'm doing with the Kinect is similar in profile. What I'm observing calculate as a profile as those armbands would capture, but there is some differences. And it depends on heavily on the motion type. So if you write an application, what you want to do eventually is to correct not just with this formula, which I did in my case. I corrected my formula and made it a little bit better. But in the end, what you want to do, you want to have formulas for those energy expenditure estimations or detecting motion in general that's dependent on the type of motion you're expecting. Yeah, that's the guidance we give. Well, that was a lot of content to cover, a lot of ground to cover. And I hope it helped you to understand a little bit how to develop software, where to ask questions for it, and what you can do with it. Yeah, this is all I have as a content. If there are any questions, I rely on the moderators to ask them now. Want to thank the sponsors again. Really, really thank you, sponsors. And there's also feedback you can provide. All right, I went 2 minutes over so far. If there are questions, please address them now.